Okay, now let us look at third scenario. In the third scenario, this is a production line with a single bottleneck and machine failures at all workstations. So let us consider these cycle times, 10 everywhere except at the fifth workstation. So what I will do now here, I assign 10 as a cycle time at every workstation except the fifth one where it is 14. And let us keep this inventory limit as 5. And there's only one machine at every work center. And let us go to the resources. So let us set a failure pattern and repairs. For example, each resource has a failure rate of 0.01. And we assume that the failures follow exponential distribution. And we can change that later if necessary. And the failure rate is 0.01. It means that the average time to fail is 100 units, 100 minutes here. And to keep it simple, let us assume that there's a fixed repair time. You can take it at random, no problem. You can also assume exponential distribution for repair time also. But to keep it simple, I take a fixed repair time for every machine. And let us ignore that calendar. The resources are available all the time except during the repair time. So now let us simulate this scenario. So let me create the jobs accordingly. Note that there's a bottleneck. I'm going to simulate. Now, the average daily production is 85.31, and the system is producing 60 instead of 14. One piece every 14 minutes. It is taking 16 minutes on the average to produce a piece. This is the average WIP. The reason is when you look at these cycle times, if there's no machine failures, no repairs and all, this should produce how much? Let me see that. It has to produce the daily about 102.86 pieces, but it is producing only a few of them, only this, because of these failures and repairs. So what can we do? So now the question is here. This our goal is to set optimal inventories without losing productivity. So right now, we set inventory limit 5. So do we really need inventory limit 5 while implementing pull? We can simulate. For example, if I take only 2 pieces, if I allow only 2 pieces to wait at any time at any work center and simulate that, that could be watts. So this is slightly one. But I'm doing, in fact, I need to do for enough more pieces. I'm sorry, I forgot that I had to do for 5,000 pieces because of the randomness. So I'm going to simulate now this production for 5,000 pieces. So it takes about 12 seconds to simulate 5,000 pieces. So here the product, we are getting 86.46 pieces per day from this line. Now what I will do, instead I will put 5, the inventory limit 5. Then I expect more productivity. So let me simulate this scenario. So here I'm getting 89.53. But what I would expect, because of the failures, we can get at most 89.5. This is close to that. But right now, the average inventory is 22.73, and we allowed up to 5 pieces to wait. There's a possibility we can reduce this limit at some workstations and again not lose any productivity. So for that purpose, I did some experiments and I found that these are good enough. 2, 2, 3, 5, 4, 2, 2. So what I will do is here 2, inventory limit 2, and here 3 and 5, 4, 2, 2. Even if we take these inventory limits, we don't lose productivity. I'm going to simulate this production line with these inventory limits in a pull system. So each time is taking about 13 seconds because of this demo. Otherwise it will take normally 12 seconds. Okay, now we got 88.95. Close to 89. If you run a few more simulations, you get 89. But if you're not happy with that, you can increase that. For example, let me make it 4 here and simulate that scenario. So I'm increasing the WIP limit at the fourth workstation by 1. So there you can make small adjustment there to be more confident. Yeah, 89.83. So yeah, I would say that this is pretty good. So if you maintain inventory limits like this, then we can have whatever is possible. That is 89.5 pieces per day here. So the average WIP is 59.9, almost 16. So I would say these are the optimal inventory limits so that the WIP is under control, WIP is minimum. At the same time, we don't lose productivity. So this is the scenario 3.